Then we need to break this process, break this entire ribosome apart so that we can reset this. And so to do that, we are gonna need this protein called RF3. RF3 is GTP bound, and RF3 is gonna bind to the ribosome and facilitate the removal of RF. And when that is removed, RRF and EFG also come in to break apart the complex. I know I'm not showing you a complete diagram of the steps for these two, but I will say that that's not super necessary, and you should just remember it as RF3 GTP, RRF, and EFG break apart the complex. And it is the hydrolysis of RF3 GTP and EFG that power this process. And if you want to think about the cost, the parts that cost, RF1 doesn't cost anything. RF3 is GTP bound, so that costs something. And then also remember, EFG does. So as a result, you have these two steps that cost GTP to happen. And so as a result, when you're terminating a protein, you consume 1 GTP per protein, or you consume 2 if you consider EFG as well. So, and this is a fixed cost. This only happens once in a protein. Okay, just making sure I'm recording. All right. To the next one is just a summary of the costs. So here I put a table to make it helpful for you guys. So let's analyze and use an example. So let's say I'm making a 100 amino acid long protein. Actually, let's make it 101 because I suck at math. 100 amino acid long protein. What is the cost of making this protein? So you need to make 101 tRNAs for each one. So we will say 101 tRNAs, which will give me 101 ATP. Because remember from last recitation, charging a tRNA costs 1 ATP. Now I put a +1 here. The reason is that the first amino acid is N-formyl methionine. And so as a result, some people consider that as an extra cost. So because and there's N-formyl methionine, what I would do then is say +1 for FMet, and then that gives me 102. All right, so we have 102 ATP now. And that's pretty much the only ATP cost. So we would say final cost 102 ATP. All right, let's move on to the next one. Initiate. To initiate, IFTU needs to be GTP bound. So that's the one. To elongate. So if we have 101 amino acids, that tells you that you're adding 100 amino acids to the first amino acid. So that tells you 100 elongation steps. There's 100 elongation steps, and each step requires 2 GTP. Then that tells you 2 times 100, which leaves you with 200 GTP. If you didn't want to do that, 2 steps. If you didn't want to do that mental math, you can just plug and chug using this equation. 101 minus 1 is 200. So this n being the length of the protein. If you want the kind of like logic, you can just think of it as if you have a 101 long protein, you add 100 times. And so as a result, 100 elongation steps, each step has 2 steps of GTP, hence 200 GTP. And then to terminate, you use 2 GTP because that's for the RF3 and EFG. And so our GTP cost then is 1 GTP plus 200 GTP plus 2 GTP, which leaves you with 203 GTP. And so 102 ATP, 203 GTP is your final total. And you can use this shortcut as a guide. One thing to note, some textbooks consider initiation or the tRNA charging. So if you remember tRNA charging, I will go back very far. tRNA charging uses the step where ATP gets converted to AMP. In some textbooks, they consider that as one ATP used up. In some textbooks, they consider ATP to AMP as 2 ATPs used. So whenever you're reading a different textbook and you see this kind of notation where like they say this is 2 ATP used, I just want to make sure that you guys are aware. For us, we can just consider it as 1. But for some textbooks, they do consider it as 2. Okay, so that's for translation. What's important for you to know, in my opinion, is to make a list of all the proteins that are involved. For initiation, know what each IF does, what the costs are, and why it's important that it happens this way. So an important question just might be like, why would it be bad if the 50S bound to the 30S immediately? And then the answer to that might be the tRNA in the starting codon might not be able to fit in the P site directly if that's the case. For elongation, the same thing. There are a lot of proteins. Make a list of the proteins that are necessary and which one of them needs energy and which one of them does what job. I would really understand why it makes sense, this mechanism, why it makes sense to transfer the growing peptide to the A site tRNA, and how that facilitates this kicking process, and that's why we don't lose the growing peptide. And then for translation, just proteins, pretty much. And if you can think about these mathed as like a formula, I think that should save you some time analyzing it instead of thinking about the logic at all steps. For sugar, we covered this right before the end of the in-person semester. So all of these slides are present in my last ones, but I would put them in here just for reference. Here are the sugars for reference. Here's how you name a sugar. Here's how you form a ring. And then here's how you name oligosaccharides. But what we learned today, hopefully that's new, is polysaccharides and energetics. So if you have any questions in here, refer to my recitation slides, to my practice problems, or if you're still confused about like what's a reducing sugar, what's a non-reducing sugar, what's an aldose, what's a ketose, what's a alpha, what's a beta, just email us and we'll try to answer it on a case-by-case basis or attend office hours. So what's new from the newest Bender Hayden lectures is polysaccharides. So when we talked about sugars, we said that there's an alpha and beta way of bonding. So before, we talked about the anomeric carbon, which I will look using this image here. When glucose forms into a ring, it can either have alpha D-glucopyranose, where the OH is on the opposite side as the bulky group, or it could be on the same side as the bulky group and considered beta D-glucopyranose. So this is naming alpha and beta-ness in terms of one sugar. There's another use of alpha and beta in sugars, and that is describing how polymers chemically bond. If you have a long chain of polymers of sugars like this one, so you can imagine there's more sugars on the left and on the right. We look at their ester bond and ask in which direction do they point. In this ester bond here, the oxygen bond, the carbon-oxygen bond points down for one sugar, and it also points down on the other sugar. And so in this case, we would say that this sugar, in this bonding, that these glucose subunits have their O's, the glycosidic bonds pointing in the same direction. And so we would call this an alpha linkage. And you might be confused because there's the letter beta right there, but this beta is referring to the fact that um, the bulky group and the anomeric OH are on the same side, hence it's beta. But when we're referring to the sugar as a whole, you look at the orientation of the bonds between the sugars. And if they're on the same side, that's alpha linkage. The beta linkage, on the other hand, would look something like this. If I have this sugar right here and this sugar right here, oxygen in the middle, one glycosidic bond emerges coming from the top, one glycosidic bond emerges coming from the bottom. When this is the scenario, we call this the beta linkage. Whereas alpha linkage will look something like this. Oops, I suck at drawing. Let's see here, like that. So on the same side, alpha linkage. So make sure you differentiate this between alpha and beta in the anomeric carbon. Those are different. Alpha linkage in terms of polysaccharide refers to this. And one thing to note, when you have a alpha linked sugar, the shape they create is often something like this, where the sugar ends up such that it starts curling around. And that's usually the most stable shape for alpha linkage. For beta linkage, the final shape ends up looking like sheets that are parallel. I know my lines aren't parallel, but they end up looking like that. And so as a result, they're very stable. And so this alpha linked sugar that's very compact and spirally, this is what our glycogen storage looks like. Whereas this beta linkage that's very parallel and stable, this is what cellulose and chitin looks like. So this is much more stronger and protective. And we don't have the enzymes to break them. So just remember, you can have a polysaccharide that's alpha linked and a polysaccharide that's beta linked. All right, so to end our recitation, let's go over bioenergetics, which is the most important part and most confusing part in my opinion. So nugget 1 and nugget 2, I think you guys are very familiar. Nugget 1, reactions occur if delta G is negative. Nothing new. Spontaneity, the rule of spontaneity is delta G negative. So I hope everyone's okay with that. Where people get confused is how enzymes play a role in that. Remember, enzymes only change activation energy, and therefore they only change your rate. So if you have a reaction A to B in equilibrium, and the ratio for that is K, concentration of B over concentration of A, and I ask you, then you add enzyme, the change in the K should be 0. The enzyme should not change equilibrium because enzymes only change the rate, not the final concentrations. So make sure you guys remember that. It's a simple thing, but trick question in the middle of an exam, very stressed, you're very tired, you're very finishing the exam. And then we'll ask you a question, I add an enzyme, will I produce more product? If I'm in equilibrium, the answer is no. So I hope nugget 1 is good. Nugget 2, if a reaction is endergonic, you usually have to couple it with an exergonic reaction for it to occur. So if I have a reaction, I'm going to give you a general just example if this is unclear. A plus B results in C, and let's just say that delta G of that is +5. So this reaction isn't going to happen without any outside input.